In this lecture, we're going to examine the topic, the power and intensity of a sinusoidal sound wave, and also the concept of sound level, measured in decibels. In the textbook, they derived the power and intensity of a sound wave using the formula of power equals to the product of force and velocity. So they started with P equals to F dot V. Okay, so this P is not pressure, it's power. Certainly that is a valid way of finding the result, but in this lecture, we're going to approach this from a different angle, and you can see the result is actually going to be the same. So what we're going to do is consider a column of air in which there's a sound propagating from left to right. And we have a cross-section area A. We wish to figure out how much energy passes through this area per unit time. And that, by definition, is the power going through the area. Okay, that is energy passing through per unit time. And if we divide this by the area, then we get power per unit area. And by definition, that is intensity. Okay, so let's figure out how much energy will pass through this window of cross-sectional area A, which is highlighted in yellow. You know, in order for the energy to pass through, you're looking at a portion of the wave that is located close enough to this cross-section, to this window. Otherwise, it wouldn't be able to make its way across this cross-section area over time dt. Okay, so in order to make its way over this area, you have to be close enough, and you have to be within the cylinder of height v dt, v being the speed of the wave. Okay, so you have to be within the cylinder. Question is, how much energy is within the cylinder? Okay, let's say this much energy is dE. Looking for dE. Okay, now we know that basically we're looking at a whole bunch of simple harmonic oscillators, assuming that we're looking at a sinusoidal wave. Okay, wave is basically a collection of oscillators, in this case, simple harmonic oscillators, which will result in simple harmonic wave. So for each oscillator, I have the energy is equal to the sum of kinetic energy and potential energy. We also know that per cycle, the kinetic energy and potential energy have the same average value. Okay, they're equal, they each equal half of the total energy per cycle on average. So let us concentrate only on one of them. Let's say the kinetic energy. Let us find the kinetic energy possessed by the oscillators in this region, and if we double that, we'll get total energy. Okay, now, what is the kinetic energy of a particle of mass m moving at speed v? That is 1/2 mv squared, right? Now, let's consider a region of volume dv. Okay, within this volume, what is the mass? dm. Well, dm equals to rho dv. Rho dv. Okay, and let's say the speed of the oscillators within this region is v. Is u. Now, please do not use the letter v, because v here stands for the speed of the wave propagating. It is not the same as the speed of a particle of an air molecule going back and forth in association with sound, with the oscillation of the sound. Okay, v does not change. V is the square root of b over rho. It never changes. But u, the speed of the particle, can change all the time as a function of distance, location, and a function of time. Okay, so we're looking at u. So u is, of course, partial s, partial t. Okay, s is the displacement associated with the sound wave. Right. So for this particle of mass dm, I have dk, which is 1/2 dm times u squared. Okay, so that's dk, the energy possessed by this mass dm. So that is 1/2 rho dv, and then times partial s, partial t squared, right? And so what is the total energy, total kinetic energy of all the oscillators within this region? Well, then I would have to integrate over dk. Okay, I have to integrate over dk. So when you integrate over dk, what do you get? You will get 1/2 rho partial s partial t, and you square that, and then you have to integrate over dv. Okay. Now, s is a function of location and time. Okay. So when you square that, when you take derivative, it's still a function of location and time. But what I can do, of course, I can actually work out what s is, because I know s is a sine or cosine function of time. I can work it out. But what I can also do is I can take the average value of partial s partial t over this region. Then I don't have to integrate anymore. I can just go 1/2 rho partial s partial t squared average over the volume, and then times the volume itself. Okay, I can do that. Okay, that way I don't have to integrate. Now the textbook actually did this integration of a sine or cosine squared function. You can do that, get the same result, but guess what? It is not necessary. There is a simpler way of doing that. Let's see how we can do that. Okay, s equals to, as you know, s maximum, either sine or cosine function. The textbook uses, let's see, does the textbook use a cosine function or sine function? Let's see here. So the textbook uses a cosine function. It doesn't matter, sine or cosine, they differ by a initial phase, that's all. Cosine of kx minus omega t. Okay. So that's the sinusoidal wave. And then we're going to take a derivative, partial s partial t. You get negative s maximum and omega, and then sine function. Okay, kx minus omega t. All right, and you can square that. So then you get k for this volume v equals to 1/2 rho. And then you have to take the partial s partial t, you have to square that. So let's do that. You get x maximum squared, omega squared, and you have volume, and then you have the sine squared, right? Kx minus omega t. Now remember, I have to take the average value. Okay, I have to take the average value. So what is the average value of the sine squared function? I mean, you can integrate, right? And it's just 1 over period, then integrating the sine squared function from 0 to t, the period, dt, and you can find the result. But it is not really necessary to do that, because I know that sine, this integral, this average value, I know exactly what it is. Okay, I know equals 1/2. How do I know that? Because you know sine squared plus cosine squared equals 1 for any argument, right? For any angle, that equals 1, right? And I take the average value, that still equals 1, because the average value of 1 is 1. But if you average over the sine function or cosine function squared for 1 period, you're going to get the same average value, whether sine squared or cosine squared. The average value is the same. So therefore, each must be equal to 1/2. See that? If you don't believe me, just look at what the textbook does. It actually finished its integral and got that result of 1/2. So it is not necessary for us. Okay, so this average value of sine function equals 1/2. So therefore, so what we're actually getting is k average. Okay, so k average, and if I plug in the value of this 1/2, so that is 1/2 rho amplitude of displacement squared, omega squared, and then times another 1/2, so it actually becomes 1/4. So this is 1/4. And then v, what's v? V in our case, v is the volume of the cylinder, which is A times v dt. Okay, so A times v dt. Okay, so all this kinetic energy possessed by these oscillators, all this energy will pass through this window of cross-section area A over time dt. What is the total energy that will pass through? It's double that, because again, we're looking at a whole bunch of oscillators, simple harmonic oscillators. They each have half of the energy being kinetic, the other half being potential, and they're equal on average. And therefore, the total energy E that passes through would be 2 times the average value of the kinetic energy, that's 1/2 rho S maximum squared omega squared A V dt. Okay. Again, this is all the energy passing through this window, all this energy passing through this window over time dt. So what is the rate at which energy passes through? Then you have to move everything, you have to divide everything by dt, right? So then you get the power, you get the average power. And what is that equal to? Just divide this by dt, so you get 1/2 rho S maximum squared omega squared A V. Okay, there's no dt anymore. All right, and furthermore, if you divide both sides by the area, then you get the amount of energy, amount of power passing through per unit cross-section area, and that, by definition, is called intensity. So the intensity is the concentration of power over the cross-section area. Is defined as P over A. Of course, I'm looking at the average intensity, and that equals 1/2 rho S maximum squared omega squared V. Okay, this is an important expression for the energy, for the intensity of the sound wave, given its density of the medium, given the amplitude of the displacement wave S maximum, and angular frequency omega, and then the speed of wave. Okay, so that is the same expression as you can find from the textbook. The textbook also has this expression was derived in a different manner. Okay, it was derived from F dot V. So we have a slight different derivation. I want you to know both so you get a better understanding of what's going on here. By the way, I can also rewrite this expression instead of S maximum. I can rewrite in terms of the amplitude of the pressure wave, because you know the pressure and amplitude are related. Okay, so I have, remember, you recall that delta P equals what? Negative B partial S partial X, right? So if I express S in terms of the given cosine function, which is S maximum cosine of kx minus omega t, so I'm looking at the special case of sinusoidal wave, then I can find delta P. It is going to be B S maximum omega, actually K, because you're taking with respect to X, not to T, so it's actually K here. K, okay, then you have a sine function. Kx minus omega t. Now, this part, the part that's in front of the sine function, that is the amplitude. Okay, that is the amplitude of delta P, and that is, I'm going to highlight this, that is what? That is the amplitude of delta P, which is delta P maximum. So I'm going to rewrite this, I'm going to highlight that part as V maximum, okay? Delta P maximum. So I have delta P maximum, the amplitude of the pressure wave, equals what? B S maximum K. See how they're related? The amplitude of the displacement wave and the amplitude of the pressure wave, they're proportional to each other, which makes sense because when the particles move with greater amplitude, they're going to compress and decompress the air more, and therefore causing greater change in the air pressure. Okay, now I know what K is. K is 2 pi over lambda. So I can rewrite this as 2 pi over lambda. And lambda itself is the speed of the wave divided by the pressure, the volume. or what I'm talking about, divided by the frequency, okay, V over F. And you flip that F over to the numerator, you get 2 pi F, which is omega. So I can rewrite this as B omega S maximum over V, okay? You can also find this relationship in the textbook. So you can, in this case, you can rewrite the average intensity as a function of delta P maximum instead of S maximum, using this expression to replace S maximum with delta P maximum. So let's do that. It is equal to 1/2 rho omega squared V, and then times S maximum squared, but S maximum itself is equal to V delta P maximum over B omega, and you square that, okay? And let's see what we come up with. Then you're gonna get 1/2 rho, and then omega squared is gone. You have V to the power 3, and you have delta P maximum, okay? Squared, right? And there's a B squared. Now, don't forget, B is in the expression for V, okay? I have that V squared equals B over rho. Remember that? Okay, so I'm going to replace a V squared with B over rho. Then I have 1/2 rho, and then you have one V left, and there's a V squared, which is replaced by B over rho. Then you divide it by B squared, and then multiply by delta P maximum squared, okay? So let's simplify that, all right? Let's simplify that. Rho is gone, and you still have one V left, 1/2 V and then you have delta P maximum squared. And then you divide this by B. There's one B left. And then let me clean up one last step. From here you can see B equals V squared times rho, okay? So rewrite B as V squared times rho, so you get V over 2 V squared times rho, and then delta P maximum squared. You cross out the power of V, and you get an alternative expression for the average intensity as delta P maximum squared over 2 rho V. You can find this expression in the textbook as well. So there are two alternative expressions for intensity, one proportional to S maximum squared, the other proportional to delta P maximum squared. And clearly, they're equivalent to each other, and they offer a different way of interpreting where the intensity comes from. It is due to either the amplitude, either due to displacement wave or due to the pressure wave. They're really related to each other. All right, so this is how you find intensity. Now, what's really important to us from a from a practical point of view is how loud the sound is. We know that the greater the intensity of the sound, the louder we're going to perceive it, right? Assuming everything else being the same, such as the frequency. When we hear the same intensity signal at different frequencies, our ears have different sensitivity to different frequencies. We can only hear a certain range of frequencies, and we're more sensitive to the middle of that range. But let's not talk about the issue for now. Let's just talk about given the same frequency, when you increase the intensity, you are going to certainly increase the perceived loudness. Okay, so something more intense, the sound source is more intense, certainly more powerful. We're gonna find this to be louder. But is it true that the perceived loudness is proportional to the intensity. That is, when you double the intensity that we hear, does it appear to be twice as loud to us? You might think that's the case, but the answer is no. And there is a reason why the answer is a no, because our ears actually have a protection mechanism in place. Look, according to research, a normal pair of human ears can hear something as faint as 1 picowatt per meter squared. Okay, so this is the lowest intensity signal that we can possibly hear for a normal pair of ear. 10 to the negative 12 watts per meter squared. That is incredibly small amount of intensity. That tells us how sensitive our ears are. Okay, you can calculate based on this minimal intensity what kind of amplitude of displacement that corresponds to that, and what kind of amplitude of pressure that corresponds to that. It's not going to be a lot. Okay, we can do a little calculation. We can find that result. You know, if we use this formula here, there is a squared here. We can go ahead and find delta P maximum, or we can replace delta P maximum with S maximum or SM. And then we can find the corresponding S maximum. In fact, I think it's actually more dramatic if we actually simply calculate the maximum displacement of air molecules as a sound wave, which will give us this minimum intensity that our ears can barely hear. Okay, so I have I minimum equals to I have to express in terms of S. So going back to here, this formula. Okay, 1/2 rho S maximum squared or omega squared V. All right, so let's do that. So we have to know what density of area. That's 1.29 kilogram per meter cubed. And omega, that has to do with the frequency. It's actually 2 pi f. So let's assume it's 1,000 hertz. Okay, that's a typical frequency that our human ears are pretty sensitive to. All right, and so we have that, and then so rho equals 1.29 kilograms per meter cubed. The speed of sound is 331 meters per second. And omega is 2 pi f. And let's take f as 1,000 hertz. Readings per second. So you get all these numbers, right? And you will, of course, you know what I maximum is. I minimum. Okay, I minimum. That's the threshold of hearing. 10 to the negative 12 watts per meter squared. You can then go ahead and calculate S maximum. Okay, so what is the amplitude of the displacement wave of the sound that we can barely hear? So S maximum. Go ahead and solve that. Okay, so that is equal to 2 times I minimum divided by rho omega squared V, right? And do this calculation. In fact, the textbook does that for us. There is a sample problem in which they did this calculation. And the answer turns out to be 1.11 times 10 to the negative 11 meters. So it's about 1 times 10 to the negative 11 meters. Wow, negative 11. Have you ever calculate a length that small in all the 8 series classes you have taken so far? Probably not, okay? And you're gonna see smaller numbers, smaller lengths later, but this is probably the smallest so far, 10 to the negative 11. How small is it? Let's put it in perspective, okay? The smallest atom of all, of course, is the hydrogen atom. It's got only 1 electron, not 1 proton, okay? The diameter of a hydrogen atom is of the order of 10 to the negative 10 meters. This is 1/10 of the size of a hydrogen atom, the smallest atom there is. When the air molecule oscillates only by an amplitude which is 1/10 of the smallest size of all atoms, we can already hear it. Okay, that's how sensitive human ears are. Okay, when we talk about energy or intensity of the sound wave, typically it's very, very small. Okay, because our ears are so sensitive, it can pick up those incredibly, incredibly weak signals, 10 to negative 12 watts per meter squared. And on the other hand, our ears can also tolerate much stronger, much more powerful sound. In fact, again, for normal people, the maximum intensity we can tolerate is about 1 watt per meter squared. Okay, 1 watt per meter squared. So that was I minimum, the threshold of hearing, but the maximum we can hear, we can tolerate before our ears start to get permanent damage, it's a 1 watt per meter squared. You compare that to the minimum value of 10 to the negative 12 watts per meter squared. You look at 12 orders of magnitude. 12 orders of magnitude. So our ears are not only sensitive, but extremely flexible. We can pick up extremely faint signal. We can also tolerate much, much stronger signal with a with a range of 10 to the 12 or 12 orders of magnitude. Have you ever seen any other physical quantitative studies so far that has to do with human perception that can cross 12 orders of magnitude? This is just incredible. But you know what that means? The loudness cannot possibly be linearly proportional to the intensity that our ears intercept. Because if that is the case, then the strongest sound we can tolerate will be 1 trillion times as loud as the weakest sound. Do you think that's the case? No, because if when you double the intensity, then our perceived loudness doubles. Then when intensity goes up by a factor of 10 to the 12 or 1 trillion, it's going to break our ears. There's no way our ears can tolerate that kind of 1 trillion times the loudness. Okay, it can tolerate 1 trillion times the intensity, but certainly not 1 trillion times the loudness. The way our ears protect itself is to get less sensitive when the intensity picks up. Okay, it's still going to be louder than before if the intensity goes up, but it doesn't grow. The perceived loudness doesn't grow linearly. All right. So if I were to imagine if there's a perceived loudness, which is a function of intensity, I, okay, it's not going to be linear function. No, a linear function would look like this. Would look like this. Let me draw a picture, draw a line like this, right? So when intensity is 0, it doesn't register at all. And then when intensity doubles, the loudness also doubles. That is a linear model. But like I said, that's not going to happen. It's not a good thing, because that would mean that, again, the strongest sound we can tolerate will be 1 trillion times as loud as the weakest sound we can hear. Our ears won't be able to tolerate that. In reality, our hearing is not perfect, meaning that when the sound, even though the intensity is not quite 0, but it's so faint, there's a point where we cannot hear anymore. In fact, as you can see, there is a minimum intensity, which is 10 to the negative 12 watts per meter squared. Below that, we cannot hear anything. So the perceived loudness will be 0 at that I minimum. Okay, so an I minimum, which is 10 to the negative 12. We cannot hear anything. Or we can barely hear something. Loudness just barely above 0. All right. But then from that point on, are you going to get a straight line? No, because as the intensity grows, the loudness does grow, but it shouldn't grow as a straight line. Rather, it should look like this. Like this. Okay. So it does grow, but in order to protect our ears, It doesn't grow linearly. It should grow at a slower pace than the intensity grows. Now, question is, what kind of function is this? It's not a straight line, right? What kind of function is this? Have you ever seen a function like this? It starts at a certain point where the value is 0 and it climbs like this. Well, you probably recall what that is. That does look like what? A log function, right? A log function. So it makes sense that it is a log function. Now, exactly why is this log function? Why is our perceived loudness a log function of the intensity? This subject goes beyond physics. It has to do with physiology. It has to do with how we perceive loudness, human perception. This is not just physics, okay? But experience tells us, research tells us that our perceived loudness is really pretty accurately represented by a log function. So this red curve, in fact, is a log function. And in this sense, we don't call it loudness. We give it an actual term in physics. We call it sound level, okay? Sound level. So we cross that out. Loudness is not an accurate term in physics because it is a perceived quantity, has to do with physiology. In physics, we call it sound level, or SL. But suffice to say that our perceived loudness is related to, not only related to the sound level, we can pretty much say it is a linear function of the sound level. Okay, so this is a log function, but exactly what is the mathematical expression for that sound level SL? Here is the mathematical expression. The sound level SL is log of the intensity divided by minimal intensity. Why do you have to divide by minimal intensity? Because you can see clearly as I equals I minimum, you got a log of what? Log of 1, right? By the way, the base is 10, okay? The base is 10. Sometimes we don't even write down the base if it's 10, which we just agree it's by convention is 10. When I equals I minimum, the argument in the log function equals 1, and log of 1 equals 0, as everybody knows. Okay, so it makes sense to divide it by I minimum. This quantity on the right-hand side of this equation is a unitless number, okay, because it's just it's a log of something. It doesn't have any unit. But there are many other unitless quantities in physics. Even though most quantities in physics do have units, some do not have units. How do you know this particular number, unitless number, is not just any number? It is it represents the sound level. Well, we give it a special name. We call this unitless number Bell, B-E-L. Okay, so it's 2 Bell, 3 Bell, or whatever. But if you use this definition, you'll find that you often, the quantity that you get, the sound level expressed in Bell, often carries decimal points like 2.3, 5.6, and so on. And that's not very convenient. So what we want to do then is to multiply this by 10. When you multiply this by 10, the number becomes 10 times as much, but the unit becomes smaller. It's called decibel. Deci, as you know, is 10 to the negative 1. So 1 decibel is 1/10 of bell. Okay, so 10 decibel is the same as 1 bell. That's because we multiply by 10, so it makes sense. Okay, and decibel has also a shorthand, dB. Many of you have seen this before. Okay, so decibel is the most commonly used unit of sound level, even though it's not a bona fide unit. It's just a signature telling you that this number that you're getting, like 70 or 80, whatever, it's not just any number. It represents the sound level. Okay, then we call it 80 dB or 70 dB. dB again standing for decibel. Okay, so this is the definition of the sound level. It, according to research, it pretty much mimics how our perceived loudness goes. Okay. Now that is important because it tells us what will it take to for something to sound twice as loud? And what would happen if, two people speak instead of one, so that the intensity doubles, because you have let's say you have two identical sources producing the same intensity, so the total intensity becomes 2I instead of 1I. What happens to perceived loudness? Do you think that when two people talk simultaneously at the same intensity each, do you think that the perceived loudness also doubles? Well, not anymore, right? Because when you double I, you're not going to double the perceived loudness, because our ears becomes less sensitive when the intensity increases, right? It's not a linear function, but by how much does the loudness increase? Well, here's the deal. Turns out that roughly speaking, when the sound level increases by 10 dB or 1 bell, 10 dB is 1 bell, the perceived loudness pretty much doubles. Okay, so for something to sound twice as loud, it has to have a sound level with an extra 10 dB. For example, a 20 dB sound sounds twice as loud as a 10 dB sound, and a 30 dB sound sounds twice as loud as a 20 dB sound. So what does it take to increase sound level by 10 dB? Well, suppose you have two sound sources, one with intensity I1, the other with intensity I2. Okay, I can find sound level for each one of them, right? So I get SL1 and SL2, right? So get SL1 equals to 10, then log of I1 over I minimum. Then I have SL2, the second source, the sound level is 10, then log of I2 over I minimum. What is the difference in the sound levels of these two sources? You just take difference, right? So delta SL, what is that equal to? We just take the first one, the second one, but log of x minus log of y is not equal to log of x over y, right? So this becomes natural log of 10 times log of I1 over I2, I minimum is gone. See that? I minimum is gone. Okay. So this formula is very useful for us to answer the following two questions. Question number one. What does it take to double the loudness? Well, again, for doubling the loudness, you're looking at a change in sound level of 10 dB. Okay, so to answer the first question. Answer. You have to let delta SL be 10 dB. Okay, so that means 10 log of I2 over I1 over I2 is equal to 10 dB, which is just 10. Both sides are dB. Okay, right? So what does that mean? It means this log function equals 1, and therefore I1 over I2 equals what? Equals 10. Wow. In order to sound twice as loud, you have to give me 10 times the intensity, not doubling, but 10 times the intensity. Okay, that's what it takes, 10 times. That answers the first question. So clearly, as you can see here, the louder something gets, the less sensitive our ears are, and that's not an imperfection, that's by design, okay? That is to protect our ears so it doesn't get, it doesn't get damaged, because by being less sensitive, it's less likely to get damaged. And so that's the answer to the first question. The second question, what happens when two people speak? So when looking at a case where I1 is twice as much as I2, okay? So then that's the first one, the second one. So basically you have I1 over I2 equals 2. Okay, I1 is the case when you have two people speaking at the same time. I1 is only one person speaking. And then what is the change in sound level? Delta SL, what is that equal to? That's 10 times log of I1 over I2. And that is 10 times log of 2, okay? What's log of 2? Log of 2 is roughly 0.3. So therefore, looking at about 3 dB. That's also very surprising. It says that when you double the intensity, the sound level does not increase by 10 dB. No, it increases by only 3 dB. Okay, increase by 3 dB. So for example, if one person is talking and sound level is 60 dB, what happens when both people talk at the same time? The sound level increases by 3 dB to 63 dB. That's it. Okay, 63 dB. What happens when 4 people speaking simultaneously? Again, you're doubling intensity. Every time you double intensity, the sound level picks up by 3 dB. So when 4 people are speaking, each with the same intensity output, the sound level goes from 60 to 66 dB. So with every increase in 3 dB, the sound level, in sound level, the intensity actually doubles. Okay. Now, you may have heard commercials about how car manufacturers do whatever they could to soundproof their cabin to make the ride more comfortable. Sometimes you may hear, the sound level of the cabin went from say 57 dB to 54 dB, let's say something like that. Are you impressed? Well, you probably wouldn't be. Oh, look, it was 57, now it's 54. What's the big deal? Well, guess what? It is a big deal because it went down by how much? By 3 dB. Now you understand what that means? A decrease in 3 dB means you have dropped the sound intensity to 50%. Okay, a 50% decrease is 3 dB. Or when you double it, it's also 3 dB. That's an increase in 3 dB. So that's quite an achievement. When every time you drop the sound level by 3 dB, you are cutting the intensity by half. That's quite a lot. Okay, so except our ears get more sensitive, so you don't perceive it to be twice quiet. That's the problem. But the engineers actually did achieve quite a lot. All right, so these are some examples of sound level. Now, here are some representative numbers, okay, of sound level. There's a table in a textbook as well. So here you have some representative numbers from 0 dB. 0 dB means it doesn't mean you cannot hear it. You can barely hear it. Okay, that's the threshold of hearing. And then 10 dB. 10 dB means twice loud. We perceive it to be twice loud, and that's the rustling of leaves. 10 dB. And then 20 dB means it's twice loud as rustling of leaves. 30 dB means twice as loud as 20 dB, and so on and so forth. Okay. Usual conversation, we're looking at 50 to 60 dB. Okay, if you're arguing with people, if you raise your voice, you're shouting, that's of course more than 60 dB, but usually we're talking about somewhere in the 50s. Okay, and soft radio music and piano practice and so on. And what's a very loud sound? Looking at 80 dBs or more, then it's pretty loud. Okay, at 120 dB, you're starting to feel pain. Your eardrums start to feel pain because you're shaking it a whole lot. Remember, it's a very sensitive organ, okay, the eardrum. Remember, when the air molecules oscillate with an amplitude which is 1/10 of the diameter of the smallest of all atoms, we can already hear it. That's how sensitive it is. Anything that's really sensitive is also prone to be broken. So we got to treat it nicely. Okay, do not expose your ears to very, very high amount of sound level because you're shaking the eardrums a whole lot. It may not come back anymore. All right. So that's and you also hear you also see this table is also in the textbook because when we hear things, it's not just how loud it is or the sound level. Another factor we have to consider is the frequency. Okay. First of all, the frequency, if it's too high or too low, we cannot hear it. Okay. A normal person can only hear between 20 to 20,000 hertz. It varies from person to person. Also, each person at different age, we have different range of hearing. But on average, that's what audible range is. But the frequency is below 20 hertz, we cannot hear it. Some animals can, but we cannot hear it. Okay, frequency above 20,000 hertz, again, we cannot hear it. And also, the upper limit of the threshold of hearing, as far as frequency is concerned, has to do with age. Okay, when you're young, you can hear very high pitch. But as we get older, the eardrums, just like everything else in the body, gets less elastic. So, you know, if you shake it at low frequency, it can still respond. But if you shake it at very high frequency, guess what? It loses elasticity. It doesn't want to respond that fast anymore. So as we age, the highest frequency we can hear start to drop. Okay, you're not going to be able to hear 20,000 hertz in your 50s. No, not even 19,000 hertz for most people in their 50s. So, you know, the threshold actually start to drop as we age, which makes sense. Okay, so this table, this diagram really tells you, you know, what kind of frequency range and what kind of sound level range or loudness range corresponds to normal hearing, corresponds to music, conversation, and so on. So that's something good to know. But again, this is not just physics at work. Okay, how come we perceive this type of sound as pleasant instead of noise or something annoying? That is beyond physics. It's physiology at work too. All right. So this is a lecture about intensity and perceived loudness measured with sound level in decibel. Then after this, we're going to switch gears. We'll look at an important topic in acoustics, and that is, how does the frequency of what we hear change as the source of the sound moves, or as we move towards or away from the sound? That is a phenomenon called the Doppler effect, and we'll see examples of that starting from the next lecture.